Welcome back. So we will continue giving basic definitions of the course, and before we move on to the techniques of the course. So in the last lecture we saw the following problems. We saw the following problem of vertex cover. So what was the problem of the vertex cover? So problem of the vertex cover was input was g comma k. Okay. Question was, does G has a set S such that G minus S is an independent set? Okay, set S independent set and mod S is less than or equal to k. Okay. So basically we are looking for a set S such that for every edge one of the endpoint is present in S, and that S was also called a vertex cover. And then we introduced this notion of parameter, and parameter was k, and our objective was to design an algorithm with running time f of k times n to the power big O of 1, okay, and where f could be any function of k, and dependence on input size is polynomial. Okay. And for vertex cover, we did make an algorithm with running time 4 power k n to the power big O of 1. Okay. And then we asked that in this course, we will see a lot of techniques to design such an algorithm. We will define FPT today formally, but this is the kind of algorithm we would like to design. And we said there are other for the same problem A, there could be different parameters. With respect to some parameter, the problem could be hard, meaning we cannot expect to have such an algorithm, f of k n to the power big O of 1 kind of algorithm, and there could be some other parameters for which such an algorithm do exist. So let's look at the closely related problem of we will look at the closely related problem of click. So what is a click problem? So in the click problem, input is g comma k. Question is, does G has a click of size at least k, and our parameter is k. The size of solution or the click we are seeking for, we are asking for. Okay. And what is a click? Basically, click is a graph where every edge is present. Example, triangle is a click. Example, look at all the edges are present here, right? This is a click, but this is not a click because there could be edges here which is absent, there is the edges which are. So basically a graph is called a click if look at any pair of vertex, there is an edge present there. Okay. So this is what is click. Now as we will see in the course that for this problem we will see there is no f of k n to the power big of 1 time algorithm for click, right. So, notice this field is quite interesting, that while we saw for a vertex cover there is an algorithm of running time f of k poly n, we will see that click on the other hand does not have such an algorithm. But notice, so this is just a remark, both vertex covered and click are NP complete, but in the world of parameterized complexity or multivariate algorithm, they show different behavior. So, in some sense the field also does a finer classification of NP complete problems. In fact, what can we show is even more. So, in fact, for click we can show for click no f of k n to the power little o of k algorithm, time algorithm in fact. Even this is possible unless some hypothesis fails. Okay. So, let us talk about what kind of hypothesis are we talking about for a little bit. Okay. So, notice that the world of NP completeness in some sense, let us say NP completeness world is basically on the following hypothesis. Okay. No n to the power, okay, so 1 time algorithm for 3 sat. Okay. Okay. And we can build a complexity theory or we can build a theory. So, the whole NP completeness is based on that there is no polynomial time algorithm for satisfiability, basically 3 satisfiability, where where every clause has at most 3 literals, right. And so, on the other hand, we can show click cannot have such an algorithm by assuming the following hypothesis. So, this is what is called, so in the one of the hypotheses in parameterized complexity. Okay, is that no 2 to the power little of n time algorithm for 3 sat, right. Notice that for 3 sat, for that matter any sat, you have a 2 power n plus m times big O of 1 algorithm to test whether a formula phi with n variables and m clauses are satisfiable or not, right. Okay. So, because you look at each variable, you try all Boolean assignments of 0, 1 and check whether the formula is satisfiable now. There are 2 power n of them and you can check this. But what this hypothesis tells us that look, for 3 sat we do have such an algorithm. In fact, for 3 sat you have much faster algorithm than 2 power n in terms of base of the exponent. But what it tells us that you cannot have, if you assume that you cannot have an algorithm with running time 2 to the power little of n. For example, you cannot have algorithm with running time 2 to the power n by log n or 2 to the power big O of n by log n. Okay. If you assume that you cannot have 2 to the power little of n algorithm, or in particular you cannot have such an algorithm like 2 power big O of n over log n or 2 over big O of n log n, then we will be able to show in fact that click you cannot even have any algorithm better than f of k n to the power little of k. So, imagine what is the best, what can be one good algorithm for the click? One good algorithm for the click, or the trivial algorithm for the click, is try all subsets of, try all k subsets of V of g, that is it. And in n to the power big O of 1, you check whether that forms a click or not by looking at every pair of edges, whether there is an edge or not. So, similar to vertex cover, we had this an algorithm, but for vertex cover, we did make 4 power k n to the power 1 algorithm. This was for the vertex cover. And assuming what is this? This hypothesis is also called exponential time hypothesis. Okay? We will talk about it much more in the course. Exponential time hypothesis. In fact, what we are saying that, look, not only you can't have f of k n to the power big O of no such algorithm. In fact, you cannot even have no f of k n to the power little o of k. So, hoping to do better than this is not possible. So, what we can say is, unless ETH fails, naive algorithm is best. Okay? Okay. So, this is what, so assuming these two hypotheses, assuming this hypothesis, we can start showing, so if you assume like much stronger running time for satisfiability problem, you can show much quantitative lower bounds or much more qualitatively better lower bounds on problems which are NP-hard. Okay. But now I will change my track and look at the click problem. Sorry. Okay. Now, rather than assuming this parameter, let us use another parameter. So, what is the parameter? Another parameter is delta of g. Okay. This is, what is this? Maximum. So, this let us call this parameter 2, parameter 1, maximum degree of graph G. Okay. Now, let us see what happens this then. Okay. Now, notice that with respect to this, look at any vertex V. What is its degree? Is, let us call this D, is at most D. So, if you are looking for a k size click, right, what can be the maximum click size? What can be the maximum click size? Maximum click size is, notice, a click must be in a neighborhood of a particular vertex, because we must have neighbors to all those vertices which participates into this, which implies k is less than equal to d plus 1. In fact, and every click C is contained inside closed neighborhood, contained inside N of V closed neighborhood for V in C, right. So, now our algorithm is very simple. You, for every V in VG, check if there is a click of size k minus 1 in open neighborhood of V, click C, of size k minus 1? If yes, return V union C as a clique of size k. Okay. So, if we fail for each vertex, say no click, right? Then this is easy, right? So, what is the running time of this algorithm? The running time of this algorithm is you go over each vertex. For each vertex, you try D choose k minus 1, whether there is a click of size at most k minus 1, is click of size k minus 1, and then you check whether this forms a click or not. So, that is like actually k to the power big of 1, because there are k vertex and you have to check with it. So, notice this algorithm, but what we know, k minus 1 is less than equal to d. So, this algorithm is actually n to the power 2 power d times k to the power big of 1, which is 2 to the power d n to the power big of 1, right. Okay. So, now notice that for parameterized by d, click parameterized by d max degree of input graph is fixed parameter tractable. Why? Because we made an algorithm which running time this. So, notice that for a problem there could be several parameters. With respect to one parameter, the problem could be intractable. With respect to other parameter, the problem could be tractable. Okay? Okay. Okay. So, remark, problem, same problem can be FPT with respect to one parameter and hard with respect to other parameter. Okay? Okay. Okay. I think now it's time for me to have given you some notion to define some formal definition of the formal definition that we will use in the course, just to make sure that we are on the same page. Okay. So, the formal definitions I'm going to let me give you. First is that I defined you a parameterized problem is a language L subset of sigma cross natural number, okay, where sigma is a fixed alphabet, okay, okay, fixed finite alphabet. Let us not say just alphabet, it is a fixed finite alphabet. Okay. For an instance x comma k in sigma cross natural numbers, okay, k is called the parameter, right. So, for example, okay, example, size of the solution, maximum degree of the graph. Okay. So, this is my first definition that I would like to tell you. Okay. Second, another important definition is about FPT, fixed parameter tractability, which we have using up until now in a not so like in an informal way, but let us define it formally. A parameterized problem okay, L cross N is called fixed parameter tractable or FPT. Okay. If there exists an algorithm curly A, okay, called fixed parameter algorithm called fixed parameter algorithm. Okay. If there exists an algorithm A, okay, if there exists an algorithm A called fixed parameter algorithm, okay, a computable function, this is important for us, I will tell you in a minute, a computable function f from natural number to a natural number, okay, and a constant C, okay, and a constant C such that given x comma k in L or not L, but given x comma k in sigma cross natural numbers, the algorithm correctly decides whether x comma k belongs to k, whether in time bounded by f of k size of the instance times C. Okay? That is it. So, what is an FPT algorithm? So, given a language L, if you have an algorithm A, okay, and a computable function N from natural number to natural number and a constant C, such that if you give this instance x comma k to algorithm A, curly A, then it can decide whether x comma k belongs to L or not in time f of k x comma k to the power C. For example, for a vertex cover, we made such an algorithm. We had a computable function which is nothing but 4 power k. So, given an integer k in 4 power k time, and our constant was something like 3. So, in a 4 power k times the size of the input to the power 3, we were able to decide whether a given instance belongs to has a vertex cover of size at most k or not. And the language there will be, so for example, for what is the language for vertex cover? Let us understand. So, the language for vertex cover is g comma k, g has a vertex cover of size at most k. Okay. So, now our algorithm, we made an algorithm, right, where f was 4 power k, right, and our constant was roughly like maybe 4 at most, right. So, in 4 power k times some n to the power 4, we were able to decide whether given a graph G contains a vertex cover of size at most k or not. So, this just implies even with respect to this definition, the problem is FPT. Okay. So, another thing, complexity class, okay, this is the first time in the containing all fixed parameter algorithm, fixed parameter tractable problems is called FPT. Okay. So, this is another thing which you like to remember, that the class FPT is basically all those problems for which there exists an FPT algorithm. That is it. Okay. Now, one notion which we have defined, we have said that the function f should be computable. Okay. So, what is the meaning of that? So, basically, what is the meaning that f is computable function? Okay. So, basically, if we do not assume that f is a computable function, then we get into some sort of trouble when we are trying to design reductions and hardness. So, it is better to assume, and it will not take away anything from us. So, basically, what is computable function? Function f from natural number to natural number, okay, is a computable function, if there exists some Turing machine M if there is some M which given an input x, which on every input x halts with f of x on the tape. Okay. So, basically there is an algorithm which can compute this function, that is all that it means. So, even if you do not understand what computable function is, you can ignore this aspect from this whole course. It was just to make things formal. So, if you do not understand, it is perfectly fine, just that every function or every algorithm that we will design in this course will be computable. Okay. So, let us not worry about this if you do not understand, and if you understand, this will be a useful tool to have. Okay. So, another class, so that is all the basic definition that I would like to define. Another class which has been useful is what is called XP algorithm. So, basically XP algorithm is like, so I will say that L admits XP algorithm, right, if first of all you should have f computable, another function g computable, okay, and the running time is like f of k n to the power g of k time that is it in n to the power or rather I think that we should say not this, f of k x power k x comma k, the input size, okay, g of k, right. So, n choose k algorithms are XP algorithm because n to the power k, n is the input size and this. So, yeah, so basically, so this is also a class of algorithms that, so in general for most of the problems we will have a simple XP algorithm, and the hard part will be to design whether they admit FPT algorithm or not. Okay. So, given now that we have defined everything formally, so given a problem L, so first thing that we will show that whether, okay, so what will we show? So, the flow of research is very simple, given an L, FPT or not FPT, done, okay, done. FPT, it means f of k n to the power big of 1 algorithm, get, as good f of k and as good dependence on input size as possible. Dependence on input size as possible. Okay. And so, this is what our basic goal is, and then there are some then there are other kind of things we do. Okay, if we have got some FPT algorithm with running time f of k, is this f of k and optimal? If not, can we show that we can either improve it, or under some complexity assumptions can we show that this is the best we can hope for? Similarly, in the other side, when you show that the problem is not FPT, can we find some other interesting parameters with respect to which I can show the problem is FPT, and things of the kind of questions that we will be dealing with in this course. But basically, we will be providing you tools at this point of time to show whether a problem belongs to FPT or it does not belong to FPT. And with that, I will end my today's lecture, and we will move to the first technique of designing FPT or not, in designing FPT in this week, which is called kernelization. Okay, thank you.